Hello class, hope you are doing well. In today's lecture, I'm going to talk about best trapezoidal hydraulic sections. However, as you see here, I would like to recall the previous lecture and solve an example to you. This is our example. Calculate the best hydraulic rectangular cross-section to convey Q equals to 10 cubic meter per second with morning roughness equals to 0.02 and bed slope S0 equals to 0.009. The question asks us to determine the water depth and bottom width of an economical rectangular cross section. Based on the results of previous lecture, we know that in the most efficient rectangular cross sections, A equals to 2y squared, and hydraulic radius is half of the water depth. Therefore, we can replace the hydraulic radius and area in the Manning equation with these uh, equations, in which the result should be like this. Q equals to 10 from the question we know, A equals to y squared from here, and A times 1 over n. This is our Manning roughness. This is hydraulic radius, half of the depth of flow, the power of 2/3, multiplied by root of the 0. The simplification of this equation will result the value of water depth equal to 0.87 meter, or roughly we can say y equals to 1.9 meter. And from b equals to y, this is, you remember, this is the condition of the best economic rectangular cross section. We can find the bottom width of the rectangular cross section, 2 times 1.87 will be equal to 3.74. Therefore, these two values are the characteristics of our economic rectangular cross section. However, when we are going to construct such a section, never forget that we should consider a freeboard to be ready against unwanted situations. Okay, let's go to the main materials of this lecture, which is the best efficient or the best hydraulic trapezoidal cross section. This is our trapezoid. You see bottom width is B and the side slopes given by AX. A means vertical, X means horizontal. And we assume that both sides have same angle. Therefore, X is similar in both sides. Like previous course, we should calculate weighted parameter. Sorry, we should calculate, yes, weighted parameter, then take its derivative with respect to the varying parameters. Let's see how we can calculate weighted parameter. To calculate weighted parameter, we should know these values, yes, the sides or lengths of the sides. And then we can add these lengths of the sides with the bottom width, which gives us weighted parameter. Like previous course, we should first calculate area. Then we know that area is constant. Then we can simplify the function of weighted parameter when we are going to take the derivative of the weighted parameter. Yes, as you see here, the top width equals to the we sometimes show it with T or with B equals to the B or bottom width plus 2 times of XY, where X is side slope, and y denotes the depth of the water, which is our unknown. And with respect to the shape of the canal, y should be optimized. Okay, what is the area, cross-sectional area of this trapezoid? Easily you can find cross-sectional area by summation of two parallel sides. Then you should multiply those summation with distance, which is y, and then you can divide it by 2. The result will be this. Area equals to b plus xy times y. And what is the weighted perimeter? This is our weighted perimeter. Yes, weighted perimeter equals to b plus 2 times of this length. So we should find the length of the sides. And to find the length of the sides, you know that this is y, this side equals to xy. Therefore, you can use theory of the Pythagoras in order to calculate the hypotenuse or this length. Um, Therefore, hypotenuse is equal to the root of y squared plus x squared y squared. Yes. Then you can say that L, if I say this length is L, L equals to y times root of 1 plus x squared, and we have two sides, therefore weighted perimeter equals to b plus 2 times of y times root 1 plus x squared. So our duty is to differentiate this uh, equation weighted parameter. Here you see that I have three parameters, b, y, and x. But if you remember in rectangular section, we replaced b with another function that can be come from here, and then our weighted parameter would be a function of a, y, and x, and we know that a is constant. Therefore, when we differentiate p, we will face with a simpler equation as you see here, comparing to the previous one. How we can derive this equation? Only you should find b from here. You see b equals to a over y minus xy. Then replace this b here, and finally this equation will be a weighted parameter. Therefore, p equals to a over y minus xy from b, then plus 2y square root of 1 plus x squared. Or this part, is from here. Now we should differentiate p with terms of the varying parameters. You see here I have only two varying parameters, y and x. So I started with the del p over del x. Therefore, I assume that uh, y is constant and x varies. Therefore, differentiation of the p with respect to the x from here should be 0. Therefore, I have no result here. Then derivative of minus xy with respect to the x should be minus y. You see here I have minus y. Then I should find derivative of this term with respect to the x. I have 2y as a constant or as a coefficient. Therefore, 2y should be outside, and I have to find derivative of root of 1 plus x squared, which gives me 2x divided by 2 times root 1 plus x squared. You see that I have 1, 2 in denominator, and I have 1, 2 from here. Therefore, these two will be cancelled with the 2 of the denominator when I'm taking the derivative of this root, and the final solution or final derivative would be y times 2x over root 1 plus x squared. And when we are going to minimize the weighted parameter, this differentiation should be equals to 0. Let's simplify this equation, and the result would be something like this. 2x equals to a square root of 1 plus x squared. Let's check together. If I can shift this minus sign to this side, therefore it would be positive, and then I can divide both sides by y. Therefore you see that I have just this one, 2x over root of 1 plus x squared equals to 1. Yes, that's okay. 2x equals to root 1 plus x squared, and from here I can find the x. Yes, x should be root of 3 over 3. This is my x value. Let's come back to the problem. What was the x? X is our horizontal side of the side slope. Yes, or uh, we can I replace this length here again, and if it is x, it should be 1. Yes, if it is x, it should be 1. And now I know that x equals to a square root of 3 over 3. And definition of tangent, what is the definition of tangent? Definition is of tangent is front to the side. Yes, tangent equals to front to the side. X over 1 equals to x. Therefore, tangent of theta, if it is theta, tangent of theta should be this value. Okay, let me ask you, for which angle tangent of angle equals to root of 3 over 3? Yes, you are right. Angle should be 30 degrees. This angle should be. Okay, so we know that theta is 30 degree. Therefore, if this is 30, this theta should be 60 degree. And we can say that this side here is 60, and inside of the trapezoid should be 120 degree. Therefore, this is the conclusion of first derivation. Based on this derivation, or derivation of the differentiation of weighted parameter to the x gives us the value of x equals to 1 by root 3 or root 3 over 3. Or you can say that this theta, or let's say this theta is 120. Now we have to differentiate the p with respect to the second variable, which was y. We assume x is constant, then take the derivative of each term of the equation. From the first term, del p over del y would be a is constant, 1 over y, differentiate this, and it gives you 1 minus 1 over y squared multiplied by a. Therefore, first differential would be minus a over y squared. The second term, the derivative of the minus xy with respect to the y is minus x, and you see that this is constant, this is a constant, therefore the coefficients of 2 of the y should be the derivative of this term, which will be 2 square root of 1 plus x squared. Again, del p over del y should be 0 to have the minimum value of the weighted parameter. And now we can simplify this equation to get our secondary conclusion of these calculations. From here, you see that from here, I replace the value of y in this equation, which equals to b plus xy times y. Therefore, my equation will be in this form. Minus b plus xy times y divided by y squared minus x plus 2 root 1 plus x squared equals 0. You can cancel out y and 2 from here, and the result would be like this: minus b plus xy over y minus x plus 2 square root of x squared equal to 0. And you see here that I replaced somehow, I changed the location of these terms in this form. What I did, I only shifted these negative sign parameters to the other side. And what is the result is this: b plus xy over y plus x equals to 2 square root of 1 plus x squared. Now I can make the problem a bit easier. B divided by y plus, I can cancel out this y with this y, and then I have an x here. And therefore, the new form of this equation is something like this, and it can be changed like this equation: b over y equals to plus 2x equals 2 root 1 plus x squared. What I did here, you see, I'm going to multiply both sides by y divided by 2, which gives me this equation: b over 2 plus 2x y divided by 2. Therefore, uh, I can cancel out 2 from both sides, equals to 2 uh, y divided by 2. Again, I have only y, square root of 1 plus x squared, as you see here. Now, from here, I can uh, change the terms in a way that I can calculate b. Therefore, this equation in terms of b equals to 2y square root of 1 plus x squared minus x. And you see that, let me, yes. I have a question here. I have a question before going to explain this part. Let's ask you this question. What is equality implied to you? Do we have these terms previously? Y root of 1 plus x squared, or we had b over 2 plus xy? What does it mean? Actually, uh, I think that this term is to some extent appeared here, yeah, y times 1 plus x squared, or we have this, yes. If you remember, this entire 2y root of 1 plus x squared represented the summation of two sides. Therefore, one side, the value of one side equals to y square root of 1 plus x squared. Therefore, right hand side of this equation gives us the length of side. Yes, length of the side, L. If we say this is L, the length of the side equals to y square root of 1 plus x squared. What is this part? B over 2 plus xy. B over 2 plus xy. If it is my b over 2, it means half of the bottom slope from here to here plus xy. If you this is half of the b from here plus xy. Therefore, this rectangle represent the half of the top vid. Yes, look here, this is my top vid. If I divide this by 2, exactly I can get uh, this equation, and from here I can get a conclusion. This conclusion says me that length of side equals the half of the top vid. I will uh, repeat this conclusion again in next slide, but let's see what am I going to talk here. What I did here, this is actually the conclusion of second differentiation. But if I mix these two conclusions, one from here and the second one from here, what should be done? I can, from the first differentiation, I know that x equals to root 3 over 3, yes? Therefore, I can replace this value in this equation, or let's do it after uh, changing this equation to find b. Yes, therefore, what can I write? I can write this. B equals to 2y times square root of 1 plus x squared minus x. Yes, well, therefore, if you replace these x values with their real value for the case of the most efficient cross section, you can find that b, or bottom width, equals to 2 third of square root of 3 times y. This is another conclusion of the uh, this lecture, which comes from the mixing two conclusions from differentiations. Here I repeated all the conclusions and show you some of the interesting results of these calculations. Here you see that I repeated the second conclusion, and b over 2 plus xy is this side, yes, is this side, and y square root of 1 plus x squared equals to this side. Geometrically, you may say that this length, or half of the top width, seems to be greater than side length. Yes, if it is geometrically true, therefore this shape is not uh, uh, an efficient or the most efficient trapezoidal section. From the mixing point of two conclusions, I found this value b equals to 2 square root of 3 times y over 3. I repeated this for you again in this slide, and uh, I told that half of the top width, you see, half of the top width equals to the length of side slope, or length of the side. If these two conditions are done to construct, are accepted to construct a trapezoidal, or the most efficient trapezoidal cross section, as you see here, the result would be half of a one, or one half of a hexagon. The inter-angle equals to 120, and we know that the length of this length equals to the half of the top width. Yes, half of the top width is center of here. Therefore, um, this is one conclusion. The other conclusion is that when we have a efficient or economic trapezoidal cross section with the depth of y, this y is the radius of a semicircle, which can be uh, uh, drawn in a trapezoidal. Sorry. which can be drawn in a trapezoidal in a way that it is tangent with three sides of a trapezoid. And again, here I repeated the length of side equals to half of the top width. And when both conditions are the same, you will see that this length will be equal to the bottom width also. Here I would like to close this lecture, but I will give you a homework in LMS system, and I will ask you to determine all the geometrical features like cross-sectional area, bottom width, top width, hydraulic radius of the most efficient trapezoidal channel. Okay, that's all for this lecture, and I think after with one more lecture we can complete the best hydraulic cross-section topic. Have a good day.